Okay. Hello, and hello to you who are listening. I should do the tradition. Where is that? Hello, I'm David. I'm the coordinator of the Maths Learning Centre. That'll do. Importantly, this is a revision seminar for real analysis. It's semester 2, 2017. Importantly, I am not the lecturer for real analysis, nor have I ever been. I'm the coordinator of the Maths Learning Centre, which means that I spend a lot of time talking to a lot of students about a lot of different kinds of maths, including real analysis. Here we are in semester 2, 2017. We have several different requests on the board. And I think what I might do is just sort of maybe do some problems and talk through some of the details as we go, rather than try and do an overview of things. If you want an overview of open and closed sets, I did that last year. Check it out. I really did try to organise my thoughts about it during that one, but today I haven't prepared nearly as well as that. So I'm going to talk through these things. I have had specific requests for things about sequences and series. Is that what you asked about? Yeah. Okay. So I'll talk about some of those things, and in particular sequences of functions. So I will attempt to talk about those things, but really it's just going to be examples. Okay. Which is great because I won't have to cut the video into pieces later. Okay, well, I'm just going to start with this one about open sets because I've got a feeling I know how to do that. So, why is the empty set open? All right, so I need a definition of open, please. And what does it mean to be a neighbourhood?
It means you can find an epsilon inside.
Such that what? So we've got for all x's in the set, so S is open.
Then there is a different point in S that's in that neighbourhood.
I don't know what a neighbourhood is.
So there exists it's called x0 in S,
Mm-hmm.
such that x take epsilon is less than or equal to your x0 is less than or equal to x plus epsilon.
Oh. That's totally a... Oh, crap. We're in R. Okay, that's all good. I was doing openness in like Rn. Okay, right. So so for all x in S, then there's an epsilon such that the entire interval that's centred on S of width epsilon is contained inside the set. Is that the definition?
That's what I would say.
For all there exists an epsilon so that the entire interval x minus epsilon, x plus epsilon is contained in or equal to S. Okay. Okay, so that's our definition. Okay, so you'll notice that the definition says that if there is a point in S, then something happens. Right? So since there are no points in an open set, you don't care. So just rewriting this, if there is an x in S, then it really doesn't matter what happens. That's what this is. So since there are no x which are in the empty set, it's open. So that seems strange, but there are no points in it for which that doesn't happen, because there are no points in it.
That doesn't make any sense though. This is what keeps me up at night. There's no points in there to have an epsilon neighbourhood around.
Yep. And therefore there aren't any points which don't have an epsilon neighbourhood.
That's the
It's not true.
Exactly.
and therefore it is true.
No, I disagree.
So we're going to stop arguing about it at some point, and I'm just going to move on. But I talk about it as if you say that a train system is good when it has no late trains, then a train system is good if it has no trains, because it doesn't have any late trains.
Apparently, this is based on something called vacuously true. It's
Yep.
true because
There's not enough. There aren't any things for which it's not true.
It can't be proved false.
Yeah.
how does that make you feel?
That I'm okay with it, but partly because I've gotten used to it.
So you've just accepted that.
I'm okay with it because I'm okay. I have a statement I can say that I do feel comfortable with. There are no x's in there, so it would be not open if there was an x such that all the if there was an x such that all of the epsilons produced an interval that was not contained in S. Okay, so given that, so if we found an x in our set such that for all epsilon this wasn't contained in S, then we'd know it wasn't open, right? Then S would not be open. And since we can't find any of those x's, because we can't find any x's at all, it's not open. Therefore, it is open. Yeah.
What's more interesting is that it's also closed.
We can't find any, so it's not open, and therefore it is open. In ordinary English, if you say, well, I'm not going to the party, then it often means that you still aren't. But in mathematical English, there's only one way to not something, and that is to something. So that's the way it goes. There you go. Back in Maths 1A, an empty set was convex as well.
Meaning what?
So a convex set was a set where if you pick 2 points in it, then the entire line between them is completely contained inside the set. The empty set is convex because there are no pairs of points where the line between them isn't inside the set, because there are no points.
So that would mean a set that just contains a single point
Would also be convex, yes. A set with 1 point in it is convex because there are no pairs of points in it.
A set with 1 point is not open.
No, a set with 1 point is not open, but it's just worth pointing that out. Okay, because, well, let's prove that.
What are we proving?
We're going to prove that a set with a single number in it is not open. Right, so I'm going to imagine, my first way of dealing with this is to imagine what this looks like in the hope that it will help me think about the sizes of things. Because real analysis is all about how close things are together. And so I'm going to think about, here is my point A, and it's the only point in my set. I'm going to colour it in a different colour so that I can feel that it's distinguished somehow. And then I'm going to say, okay, so we know what it means to not be open. It's not open when I can find a point in it such that for every epsilon, the interval around that point is not fully contained inside the set. Yes? Yeah. So that's why I need to negate the definition, because it's sometimes easier to talk. I'm trying to show that it's not open, so I need to figure out what not open means. Okay, so, all right, well, let me just think about all the intervals that are contained in the only point, that are centered on the only point I have. Well, they're all contain points that aren't A. And so therefore none of them are contained in the set with just A. I'm just going to call this set S just so it's easier to talk about. All right, so let epsilon be greater than, let epsilon be greater than 0. Can I turn the volume down? Let epsilon be greater than 0. Then I'm going to make an interval. Okay. And consider the interval a minus epsilon, a plus epsilon. And our goal is to show that that interval is not contained inside the set with just a in it. So I can just say this contains numbers other than a, and therefore is not contained in S, because S is just A. And therefore, there is no epsilon greater than 0 such that a minus epsilon, a plus epsilon is contained in S, and so therefore S is not open. Now you're, I don't know how paniggity the person marking your exams is, because sometimes they'll be okay with you to just go straight to S is not open from the previous statement, but it feels more complete to explicitly say that there isn't an epsilon that makes this work for that point, and so therefore it's not open, because if it was open, there would be an epsilon that made it work. Okay. Closedness is the same as openness, except with the points outside the set. Closedness is the same as openness, except you're talking about points outside the set. So a set is open when, I think that's the definition of closed in your course.
So one closed is complement is open.
Yep.
And the other is contained in little points.
Right. Okay. So I'm talking about the complement is open definition. So that's so to be closed for all the points outside S, there is an epsilon greater than 0 such that the interval is completely outside S. Because you're talking about the outside being the complement being the set that's open. Okay. Sweet. And therefore you can prove that everything except A is, you can prove that A is closed because everything except A is open, because you can always find an epsilon. Given a point that isn't A, there's always an epsilon so that the interval doesn't touch A. Okay, right. So I can think about those things, and we could go down the road of asking what ifs for hours, and that would be a good thing to do if you were studying for this course, because pure maths is nothing if not just continuing to ask what if questions. So saying, well, what if it was everything except A? What if I had 2 points? What if I had an interval? What if, and just make up things and see what you can do with them, and see if you can figure out whether you believe they're open or closed first, and then how to prove whether they are. So I would say, just like in Maths 1A, when there was a definition of being a subspace, but it was useful to know a list of things that you could tell were subspaces just by looking at them without having to do the proof, would be a useful thing for this too. It'd be good to have a list of things that you know are closed or open just by looking at them, by about the way they're written, so that you have a hope of deciding whether it's worth proving things or not. I would love a lecturer to, in an exam, be brave enough to say, decide if this set is open or closed, and then prove your decision, and not tell you one way or the other which one it was, and ask you to prove whichever one it was that is actually true. I think that would be an awesome exam question, but maybe a bit too out of left field, but it's the sort of thing you're supposed to be able to do. Look at something, choose in your mind, in your heart, whether it's open or closed, and be able to prove it one way or the other. So it's good to have a list of things that are things that are open. The empty set. The empty set. I write it like this. The empty set. It's technically not the letter phi. The tails are supposed to be shorter. Probably. The empty set, the entire of the real numbers. Any open interval, any half open interval, like any infinite interval that's open at the end that's not infinite. That would be a minus. Anything that you can construct by joining these things together, and that should be about it. So yeah, I think the intersections, I think you can do as many, even infinitely many of them as you want to union, but you can only do finitely many to intersect. I think I can prove to myself that you can't do infinitely many, intersection of infinitely many of them and end up with an open set. So any union of you know, any of any number of these, even infinite, and anything, an intersection of any finite number of these. I just want to be clear to myself that that second one is true, that I'm not allowed to do infinitely many of them. And the only way for me to be sure is to think of something that does intersect infinitely many of them, but produces a non-open set as the result. So I'm thinking about having like something like that that's just shrinking smaller and smaller and smaller. And the only way to be in all of them at once would be to be that middle point. That's what I'm thinking. So I'm wondering that maybe I could do, let Sn be from minus 1 on n up to 1 on n. Like that. And then S is the intersection of all of these things. Well, let's just do it as a proof, eh? Prove S is not open. All right. My instinct says that S is a single point, and I know a single point is not open because I just proved that. So what I'm going to do is prove that it's a single point. Okay? So I know that 0 is definitely in this set. So 0 is in Sn for every n, and therefore 0 is in big S because it's the intersection of all of them. And so if any number that's in all of the sets must be in the intersection, okay, that's where, so first, it's not good practice to start a math sentence with a symbol. Okay, so if 0 was the only point in that big set, well, small set, I suppose, if 0 was the only point in that S, that would mean that I could think of any other point and guarantee that it wasn't in S. And that would be telling me that it's only 0. So to be only 0, I need to exclude everything else. So let A be not, damn it, not be 0. Yep. Then there has to be an n such that 1 on n is closer to 0 than A. I'm just going to make it a positive number because it's going to be easier to talk about it. There is an n such that, that's badly written, sorry, such that 0 is less than 1 on n, which is less than a. And I've got people telling me that there's a name for that. Okay. Sorry, that's a capital N. Yeah, there is a capital N in double struck capital N such that that is true. So therefore, therefore A is not in this set because it's bigger than 1 on n. And so therefore A can't be in S. It would be probably a cop-out to say a similar argument shows that A is not an S if A is less than 0, but I reckon it would be okay. But
I guess you could say that if A is less than 0, then it's negative B, which are something like B.
yeah. Even better. Okay. Also, minus A isn't in this set either. Since minus A is less than minus 1 on n, and therefore minus A is not in S. So S contains only 0, i.e. S is just a set with 0 in it, and so it's not open, because we just said that a set with just one thing in it isn't open. Yes. Okay. Cool. Now I want to stop there. I could keep talking about this, but I did that last year, so I'm gonna stop there. But I guess the moral for the rest of the course is that it's all like that, right? You have to come up with something. I had a picture in my head, and I had to find a way of talking about it so that it matched with the definitions and the theorems that are true, that I know to be true. Yeah. Okay. Let's have a chat about this sine 1 on x is not uniformly continuous. On what domain? Okay. For, you know, show it's not. All right. So if I'm going to show anything, I'm going to need to use the definition, or at least a relevant theorem. Sorry?
So for showing it's not uniformly continuous, you want to negate the definition of uniform continuity.
Yep, which means I need the definition of uniform continuity.
Okay, here we go. Let f be a function.
Yep.
So A goes from the interval 0 to 1 to the numbers.
Just wait, slow down. I'm trying to find a pencil that actually works. I may switch to Texter. Stop. And so F, oh for fuck's sake. F is uniformly continuous when what?
For all epsilon greater than 0,
For all epsilon greater than 0,
there exists a delta greater than 0.
there exists a delta greater than 0 such that
Such that for all x and y being
in the domain,
yeah, where the distance between x and y is less than delta, or then the distance between f of x and f of y is less than epsilon. Does everyone agree with that? I want to check. Yeah.
okay.
That's right.
So for it, we pick an epsilon greater than 0. It's possible to find a delta greater than 0 such that whenever the x and y are closer than delta together, the f of x and the f of y are closer than epsilon together. Okay. How is that different from ordinary continuity?
We get to pick a point. Well, the delta can be dependent on the point we pick. But
Right.
it can't.
Yep. So you're saying that for in ordinary continuity, you pick the point x first, and then for every epsilon there's a delta such that for all the y's that are within delta, that the f of x minus f of y is within epsilon, which means that for each x you might have a different delta for each epsilon.
Yeah. So ordinary continuity is like it's continuous at x0 if
Yes, ordinary continuity is you consider each point separately, and if it's continuous separately at each one, then it's ordinarily continuous. And uniform continuity is that no matter where you are, if you're within a certain distance of each other, then so is the function.
I don't think we ever called it pointwise continuous.
Yeah, you just call it continuous.
It totally is.
Yeah, a good word for it is pointwise continuity. Okay. So if it's not ordinary continuous, it can't possibly be uniformly continuous. That's a good start. If it's not just straight up point continuous, it can't be uniformly continuous. But the other way around doesn't necessarily follow, otherwise why would we have different names for it? So I need to think about this function and wonder why it wouldn't be uniformly continuous.
So you negate that.
I'm not sure yet. But yes, I am going to have to negate that because I want to show it's not uniformly continuous. So let's see. To negate this, we're going to get there is an epsilon greater than 0 such that there is no delta greater than 0 such that for all this, right? Okay, so to say there's no epsilon greater than 0 such that this happens, that would be the same as saying there is an epsilon greater than 0 such that there is a pair of x and y such that that doesn't happen. Yeah, to say that it does, right, such that, and keep this, etc. So we want to show there's no delta that does this thing.
I don't think that's right though. No offense, but you got to switch it for all, so then there exists 2 points in that.
Yeah, and I'm nearly there. But this is the opposite at the moment.
Not really.
It is.
The for all goes to there exists.
I did that.
No, not the second one.
Yeah, but this one doesn't though.
Yes, it does. I did this question like an hour
So
ago.
it literally everything gets switched.
For alls go to equals, equals go for alls. I know this, I asked Daniel like 4 times.
All right.
It should be there exists an epsilon greater than 0.
Yeah, you had it right. You
For
switched
all
it.
deltas greater than 0.
Okay. I've talked about it differently to this, right? I'm not doing the procedure of negating this. I'm thinking about what it means. I'm saying,
You haven't slip the negation through that second.
no, I haven't. I said for all epsilon greater than, I've said that there has to be an epsilon greater than 0 such that there isn't a delta that does this,
Okay, yeah, no, I'm with you.
right?
Yeah.
And I'm just, my next step is to pass it through. I don't like doing it as a procedure because I don't understand the procedure, but I can understand the changing of the words. So, such that blah, blah, blah. So it's the same as saying there is an epsilon greater than 0, such that for every delta there isn't this. So such that for every delta greater than 0, not all of the xy's do this. Therefore, there has to be a pair of xy's which doesn't do that. Okay, such that there is an xy in 0, 1 with x minus y less than delta, where the f of x minus f of y is not less than epsilon. I find it easier in my head to work through it one step at a time. You're saying, well, the opposite of for all would mean that there is one which doesn't. And then what does it mean for this to not happen? It means that they all don't. And what does it mean for this to not happen? It means that one of them doesn't. And I can work my way through that. And I find it easier to think about the language than to have a mechanical procedure that says switch all of this for all of this, because I don't believe it when I do that. So other people feel comfortable doing all the switches and believing that that is the actual answer, but I don't. So I find it easier to do them one at a time. So what I'm going to need to do is I'm going to need to pick an epsilon at some point. That's hard. And I'm going to need to pick an x and a y as well once I've chosen. And then no matter what delta, I'm going to have to pick an appropriate x and y. So it would be easier for me to try and think about the shape of this function to have a feel for y. If I pick a particular epsilon, I can't get all of the function values to be within epsilon of each other if the x's and if the inputs are between each other. So I need to imagine what that function looks like in order to. Okay, so sine 1 over x. So if I've got well, sine would normally do this, and 1 over x means that this is the same as sine 1, whatever that is. Yeah, whatever it is, maybe about here. Certainly positive, because 1 is less than pi on 2. And then when I got to a half, it would be sine 2, and when I got to a quarter, it would be sine 4, and when I got to an eighth, it would be sine 8. And so what would normally happen out here going that way happens this way going that way. So it's sort of just going to get faster and faster and faster. Something like that. So my guess is the thing that's causing my pain is this bit here. Because I reckon if I stopped it earlier, it would be uniformly continuous. Could be wrong about that too, but I reckon it's this bit just here where it gets faster and faster and faster to the extent that no matter how far I zoom in, there's always a dark bit here. Yeah. Okay. So, and I reckon the reason that's going to be a problem is that when I'm in this dark bit here, even if my x's are really close together, it could be that they're at the top or the bottom of this loop. That's what my thought is. And so it seems to me that since nothing is further than 2 from each other, I should pick a number less than that, like maybe 1. Because I have a feeling that no matter which number I pick, like that I'll be able to pick two x's that are really close together so that one of them's down here and one of them's up here. That's my idea. Okay. Or possibly even better, one of them's here and the other one's up there. And I could pick the distance to be doesn't really matter. Well, sine goes from +1 to -1 no matter what's inside it, so the maximum distance from here to here is 2. I just haven't drawn it equally on both sides. Just ignore where the centre is, it's supposed to go like this.
You're picking one between like that.
Yeah. I reckon if I pick anything less than 2, I should be able to do it. But convenient number would be good. Yeah. And I think I might even have one off the top of my head now. Yeah. I'm going to pick a number, I'm going to pick a half, because I reckon I'm going to do from the centre to the edge as my distance. That's what I'm thinking. So let epsilon be a half. Okay, so now I want to say that no matter what delta is, okay, so, and let delta be greater than 0. Cool, I'm allowed to, it has to work for every delta. So now I need to find an x and a y that are within delta of each other, but such that their function value is not within a half of each other. Okay. So my guess is this. I'm going to try and zoom in really close here. And I'm going to arrange for one of them to be 0. That may be the y. And the other one to be 1. That's what I'm going to do. Maybe it would have been better to have one as -1 and one as +1, because they're going to be pi apart rather than pi on 2 apart. All right, I go back, I change this to 1. Right, that's my plan. So x and y are whatever of delta apart, less than delta apart, but f of x and f of y are 2 apart, which is more than 1. So I could have just picked epsilon to be any number less than 2 and it would have been fine. Half would have been fine too, but 1 feels better. Okay, so if y is going to produce like a -1, I'm going to need y to be like 1 over... Oh, crap. Sine is stupid. That's okay. I'm going to have to pick it to be 1 over like pi on 2 plus 2 pi k, like 3 pi on 2 plus 2k pi, something like that. So if y is equal to 1 over 3 pi on 2 plus 2 pi k, so for some k, then f of y is equal to sine of 1 over y, which is 3 pi on 2 plus 2 pi k, which is -1. Okay. Cool. And I'm thinking that if x was just a bit further on, oh, damn it. That's okay. If x was just a bit further on, it was at 2 pi, not 2 pi, 5 pi on 2, or a bit further back. I could put the x over this side as well. That would be fine too. I'm going to do that. You'll see that these proofs... then f of x would be sine of pi on 2 plus 2 pi k, which would be plus 1. Sorry? X is this one, and y is this one. Because as...
Isn't it the other way around when you define them?
It's close to 0 now, isn't it?
no, because this number's bigger than that number.
It's upside down this time.
The denominator's bigger in this number, and so therefore it's closer to 0.
Oh, that's
The diagram's not very important. I can draw the diagram on my scribble paper, and it doesn't really matter, because it doesn't actually matter what order they're in. But yes, the denominator's getting bigger, so it's going that way. Because when I drew my sign, I drew it going this way, and so that's what I'm thinking. Okay, we're doing well. All I need to do is arrange for these two numbers to be within delta of each other. So I just want to subtract them and see how far apart they are. So just because I'm not entirely sure because how far apart they are, so I'm just, that's going to be painful. I'm pretty sure though, and I'm sure I could wave my hands about it and go, I'm pretty sure that I can choose these to be as close together as I need them to be. Can I convince someone reading it that I know that there's a reason why? It's probably the Archimedean principle. Yes, I can choose, good, I can do this. Okay, so I know that there is an n in n such that 1 on n is less than delta, right? That's the Archimedean property, right? And all I need to do is choose my k so that both of these are more than n. And then they'll both be further in than delta, and therefore the distance between them will be less than delta. Yes. So choose k so that pi on 2 plus 2 pi k is greater than n, which is possible because of the Archimedean principle in the other direction. In fact, I could tell you what the k is. It's n minus pi on 2 divided by 2 pi. And then 1 on 3 pi on 2 plus 2 pi k is less than 1 on plus 2 pi k, which is less than 1 on n, which is less than delta, and I get that. And so therefore the distance between these has to be less than the distance between these. And therefore, so what we have is that 0 is less than x is less than y is less than delta. Crap, one way around. And therefore the distance between x and y is less than delta. Okay. But the distance between f of y and f of x is the distance between minus 1, which is 2, which is not less than epsilon. Done. It's not uniformly continuous because I found an epsilon, which was 1, and I found a delta. I found epsilon, and no matter what delta is, I can find an xy such that we get beyond epsilon apart for the function values. Excellent. All done. Let me just read it in forwards order and see if I can make it, if it makes sense in forwards. If y is equal to that for some k, then that is equal to that. If x is equal to that for some k, then this is equal to that. There is an n such that this is that, cool, and we choose k so that that, and then those numbers are between 0 and delta, therefore the y and the x are between 0 and delta, therefore the distance between them is delta, but their function values are different by 2, and therefore we're good. Okay, we did it. This is possibly not the only way of proving this.
There's some sequence way of doing it?
Probably. Is there a sequence definition of uniform continuity?
Well, that's sequence definition of continuity.
This would be like a Koshu sequence definition. Well, I did make a sequence. I could probably construct this into a sequence if I wanted, but I don't care. So, like...
This is really fiddly. I'm scared.
But actually, the point of me doing this was that I was capable of fiddling it till it did work. It was all based on my picture, and I was just trying to make my picture match the maths that I had to write. So I knew that the problem was here, and I knew that the reason it was going to cause problems is that my x and y are going to be close together, but their function values are going to be far apart. So I went, can I find some convenient far apart function values and attempt to squish these close together? So when would they be 1 and minus 1? That would be these numbers. And can I arrange those numbers to be close together? And what I have learned by doing this is a neat little trick. If I can squeeze both numbers between 0 and delta, then the distance between them is less than delta. I've never used that trick before. It's a nice trick. I like this trick. So one thing that we have learned... I've learned if x and y are between 0 and delta, then the distance between x and y is less than delta. That's a useful thing to know. Yeah, because it's distances, right? These two have to be closer to each other than these are because they're all inside there. And my picture in my head for that, which I was thinking but not drawing, was this, right? So there's my 0, there's my delta, and there's an x and a y in between. The distance here has to be bigger than the distance here. That was useful. I like this trick. I'm not sure if I'd be able to, off the top of my head, use it again, but now that I know about it, I'll be looking for it. Yeah, because it was what solved my problem. I went, well, what does it have to be in order for them to come out to 1 and minus 1? And so therefore, can I arrange for them to be close enough together? Yes, I can, because they can both be small. So that's nice. If two numbers are really close to 0, then they must be close to each other. Like Cauchy sequences again. Did you do Cauchy sequences? Yeah. So the concept of Cauchy sequences in the real numbers is that if the things get close to each other, then they must all get close to something, which is the opposite direction. So in the real numbers, Cauchy sequences converge. And so you don't need... So to converge, you want things to be all getting closer to a specific number. And you know that if they do get close to a specific number, they get close to each other. But Cauchy sequence theorem is the other way around. You go, well, if they get close to each other, then they must be getting close to something, like a specific number. And that's actually quite a surprise, really. But that's the major property of the real numbers that allows us to do that. The rational numbers don't do that. Yeah. But that's only because Cauchy sequences ought to converge. And so we just include all the things that the Cauchy sequences of the rational numbers converge to, and that's the real numbers. So that's one way of making them. What am I going to talk about next? Well, can someone tell me what the Bolzano-Weierstraus theorem is?
You've got a sequence that is bounded, and there exists a subsequence.
Just a second.
Every convergent sequence has every
bounded sequence
has a convergent subsequence. Oh.
What do you want to know about this? So I have questions about it. When you say it's bounded, does it have to be bounded on both ends? Okay, just checking. Right, just making sure. Because we might have been, what I'm saying is that we might have been being sloppy in our talking about it. And I just wanted to check what the full version was. So if it was an increasing sequence and you only knew that it was bounded above, it would still match, right? Because then it would be bounded below by whatever the first one was. Okay. Good, just making sure. Cool.
If it was an increasing sequence, then the whole sequence would converge, wouldn't it?
Yes.
What's the difference between an increasing sequence and a monotonic sequence?
I believe a monotonic covers both increasing and decreasing.
That doesn't make any sense.
So there is monotonic, and within that there is increasing and there is decreasing.
It defeats the purpose of the definition of monotonic. Monotonic means it means like strictly increasing, doesn't it?
Monotonic means traveling in one direction.
How can it be increasing or decreasing?
Well, if you're increasing, you're traveling in one direction, which is up, and if you're decreasing, you're traveling in one direction, which is down. And so both of them involve traveling in a single direction.
But not at the same time.
No.
It's separate.
So you can't be both. The only way to be both increasing and decreasing is to be constant. Because in this course, increasing means greater than, greater than or equal to, as opposed to greater than. Sadly. That's why they now have strictly increasing. Yeah, so you can't be both increasing and decreasing unless, so the idea is that out of all possible sequences, there's, all sequences, and then, so these are all the possible sequences, and then within that, some of them are monotonic, and then some of them are increasing, and everything else is decreasing if you know it's monotonic. And along the here, they're all the constant functions. Yeah. Strictly is everything except the boundary on either one of those. So increasing is everything including this line. Strictly increasing is everything except that. And on that line is the constant functions.
And then not monotonic.
Oh, actually, no, there's other ones. They don't have to be constant. They just have to, they could be constant for a while and then move on, right? That's still increasing. Or, yeah, depending on which way. It's still monotonic. So you are allowed to have your function, your values stay the same for a while, and that's still increasing. So I think the point is that anytime you actually have an actual sequence that you actually know its values, you'll never say monotonic, because you'll always know you'll say it's increasing. You don't need the word monotonic in that sense. But if you're talking about all sequences in a general way, then you can say monotonic to include both the increasing and the decreasing. But any one sequence will only be on one side or the other. Yeah, so it's a word that we use to make our theorems easier to state. Yeah, good. And language is the biggest thing in pure maths and real analysis in particular. Like, the reason we have these words is that we find something that we want to talk about, and it's easier to talk about it if we have a word for it. And so we go, there's this thing that both increasing sequences and decreasing sequences share. They have properties that are similar. They can be, they could satisfy Bolzano-Weierstraus or whatever. And so I need a word to encompass both of them. It's a bit like the Chinese have a word to encompass both sheep and goats.
What's the word?
I can't remember what it is. Actually,
Are you making that up?
no, I'm not making that up. Why wouldn't you? They are both animals that are kept for their fur/wool. So, and they both have hooves and they have horns, so they're very similar. Why wouldn't you call them? Why wouldn't you call them woolly sheep goats and hairy sheep goats, right? So anyway, but they don't need to distinguish between them, other than the fact that they, at the global level, they're going, do you keep any animals that you keep for their fur? Yes, I do. Do you have sheep? And then you can ask, do you have sheep or goats? But you might not care which ones you have. Right. But you don't need words for those things, you know? So you only need words for things that you want to talk about. And so I need open and close because they're meaningful to me. But if open and closed sets didn't do anything, then I wouldn't need words for them. So that's why I need monotonic, because it encompasses things that belong together and allows me to not have to say, if I have an increasing or decreasing sequence, then blah, blah, blah. I can say, if I have a monotonic sequence, and you know, mathematicians are nothing if not lazy, because they have enough other work to do. Okay, so every bounded sequence has a convergent subsequence. Well, does that come up anywhere? Like, where is that used? Presumably it's used to prove something else. Is this a theorem, or is this a thing you have to assume to be true in order to do something else?
That's a theorem, but I think it normally just sort of gets used for, like, you know, the random proofs that you get asked, like, does this sequence converge, or proof that it doesn't converge.
Okay, so you could go that.
Like one example of it, like, came up is like when you're dealing with, when you told something about the subsequences, like all the subsequences, or there exists a subsequence that does converge or doesn't converge, what can you conclude about the parent sequence, that sort of a thing.
Okay. Right. So therefore we can say, suppose you have a sequence, pardon me, that doesn't have a convergent subsequence, therefore it must be unbounded. That would be the contrapositive. Yeah, it doesn't have a convergent subsequence, so all of the subsequences are not convergent.
If a given sequence has no convergent subsequences, then it's not bounded.
Contrapositive if.
But I don't think it gets used in any, like, configure theorem.
So I think, Ben, you were trying to use it yesterday. So you go, well, this one's bounded, so let's pick a convergent sequence within it and do something with it.
Yeah, that was sequentially.
Yeah.
No, it was just bounded. Yes.
So if a sequence has no convergent subsequences, then it is not bounded. So that, so you know, is the contrapositive. So you say, well, if A then B, which means that if you don't have B, you can't have A. Yeah, which logically makes sense. Cool. If you've got a question, if you see the name of a theorem that has a name, it's not the worst thing to look through your notes and find all the places it was used, so that you can figure out what it's useful for. So far in this seminar, we've used the Archimedean property 3 times, and we used it to create numbers of a certain size, and that was what it was used for. So if you look through and say, well, where is it? If you had typed notes, that'd be useful. You could just Control F it. But since you don't have that, you're going to have to flick through. In fact, if I were doing a pure maths course now that I have said what I just said, I would probably pick a colour for each named theorem and colour code them so that I could flick through anytime the lecturer names a theorem, I'll pick a symbol for it so that I can look through, and every time it appears I will draw that symbol so that I can find when it was used. Yeah, by theorem purple.
The
It's like Cadbury that has, you know, trademarked its particular shade of purple. It's like the same sort of deal. This shade of purple.
Only 2 people in the world know the exact colour combination of that purple.
Really?
Yeah. But yeah, the Archimedean property, you use that pretty much through the entire course.
Yeah. But it's good to see, it's good to notice that it was used, but then the next level is to notice what it was used to do. Because then you can start to think what it's useful for. You can go, I noticed that the Archimedean property was useful for making numbers of a small size. And then so if you're in a situation, go, I need a small number. That's what the Archimedean property is used for, and so I'll do that. I need a convergence sequence. Excellent. The Bolzano-Weierstraus theorem will allow me to do that. Have you tried using the Bolzano-Weierstraus theorem? Have you tried turning it off and turning it on again? Sure.
There's one thing in our class exercises that I got all wrong was this.
Countability. All right. I'm not sure if that's a word. It is now. All right. So, well, so far you've already said what countableness is. It's, in terms of, linguistically, it's a word that is used to describe a set. So, I'll get there in a second. Anytime you find an adjective, you want to know what sorts of objects it's allowed to describe. Okay, and countable is an adjective. So, it's a describing word, you want to know what it's allowed to describe. And in maths, we don't talk about big and small. We're going to talk about countable and uncountable. And finite, I suppose, would be the other size descriptor. And in a way, it's a description of size, right? Description of size. So, I don't know what the definitions are in your course, but I have but the definitions I know are that finite means that, you know, the number of them, the number of things that there is a natural number. Just go away. Okay. All right, so it looks like we've got 3 sizes. Finite, countable, and uncountable. I'm sure that within each of those, within finite, there are infinitely many possible sizes. We have none and 1 and 17 and 65,536. And within uncountable, there are many different sizes. Hotly contested whether some of them are different or not, but I'm not going to talk about that. And then there is one size of countable. And it's between here and here. So, right, so these are both infinite. Or is countable a kind of finite too? Yeah. Oh, crap. All right, so just a second. There is countable. And there is infinite. And all the ones that are countable but not infinite are finite. And all the ones that are infinite but not countable are uncountable. And there is one size that is both countable and infinite.
What's that one? Countable. Countably infinite.
And that is the size of the natural numbers. Well, it's sort of defined to be the size of the natural numbers, and you discover that it's also the size of the rational numbers. also happens to be the size of the rational numbers. So we have a new way of talking about size, which is that you can put things in one-to-one correspondence with each other and then they are the same size. That's how to tell if things are the same size. So in cultures where they don't have words for numbers above 5, they still have a concept of one-to-one correspondence. So they can tell if one group is bigger than another, but they don't have words for the different sizes. And so in some sense, one-to-one correspondence is more fundamental than counting. There you go.
Actually, cultures that don't count up to 5.
Plenty of the Aboriginal cultures don't have words for numbers more than 5.
Well, you know.
But they have extremely sophisticated words for spatial arrangement of things. So, one up on us. And I don't know. If you live in a culture where numbers aren't important to you, you don't need words for numbers. So, there you go. Okay. So, we can tell if something is countably infinite if it has the same size as the natural numbers, which means that we can line it up next to the natural numbers and have one natural number for every one of them, or one for every one of the natural numbers. I believe the theorem in the notes goes, if you can create a function from the natural numbers onto it, then it's countable. And if you can create a one-to-one function from it to the natural numbers, then it's countable.
Isn't that what a bijection is called, I believe?
Yeah, but you don't need a bijection. I mean, so to be countably infinite, there's a bijection. It's both one-to-one and onto.
Right.
So, because a finite set, there is an onto function from the natural numbers to it. You just loop them round every so often. But an infinite set, so a finite set, and therefore it's countable, but there's not a one-to-one function from the natural numbers to the numbers from 1 to 5. I have to repeat the 1 to 5, at least one of them infinitely many times by the infinite pigeonhole principle. Yeah, so that's why I think countability includes all the finite things according to that definition which I saw in the notes scrolling past. Okay, so countably infinite means, so S is countably infinite means that there is a function that goes from n to s, which is a one-to-one function. Well, it doesn't have to be onto in order for it to for you to know it's. Oh no, you're right. Okay, so if there is a one-to-one function from n to s, you know it's infinite, but you don't necessarily know it's countable unless you cover the whole of s.
Isn't it?
Yeah.
I thought S had to be empty.
Sorry?
I thought the only way that's true is if S has to be empty.
What's that? A one-to-one function from n to s?
Yeah.
No. Now, imagine this function, that s be the even numbers. Let s be the even natural numbers. That sounds like a pirate. S be the even natural numbers. And then I know that this function, so f of x equals 2x, with f sending the natural number, goes from natural numbers into s, is a one-to-one function, because every natural number produces a different answer, and it covers the whole of s. And so s is allowed to be not empty, even though this is true. Yeah. Yes. Correct. Okay. No functions end in the empty set. Let's not go there. Okay. So in my head, I don't really use the definition at all. I just go, if it's the same size as the natural numbers, then it's countable. And if it's not, then it isn't. And the classic example of things that are bigger, that are bigger than the natural numbers are intervals. So let's have a list of things that are and things that aren't. So we have countable n, obviously, because it's the archetypal countable set. Any subset of n. Yep. Any subset of a countable set has to be countable, because you can create a set from the countable set to its subset by just looping round. But it's worth pointing out any subset of n is countable, so you know that it's worth trying to do it, right? The even numbers are countable because they're within the natural numbers. And the rational numbers are countable, surprisingly. It's the infinite buses, each filled with infinitely many people turning up at Hotel Infinity problem. That proves that the rational numbers are countable.
Any subset of R also countable?
Yep, any subset of Q, therefore. And uncountable the real numbers. And any interval of real numbers. So any interval, like a proper interval where A is actually let not be, is uncountable as well. Yep, the irrational numbers. And in general, if you have a countable subset of an uncountable set and you remove the countable bit, then what's left is uncountable. So if I remove the natural numbers from the real numbers, I'll be left with an uncountable set. So yeah, in general that will be true. If you remove an uncountable set from a remove a countable set from an uncountable set, then the bit that's left is uncountable. Yeah. Yes. So if I join the natural numbers to an interval, then the result is uncountable because the interval was uncountable, so it doesn't matter what I add to it, it's still uncountable. So unions of finitely many countable things are countable. I think unions of countably many countable things are countable, though that's not true. No. Yes, that's true. Sorry. No, I was thinking of the things that I was joining weren't countable, so that's okay.
Otherwise we wouldn't be able to map Q, right?
Yeah. So Q is sort of countably many finite lists. So to prove uncountable, you need to either do it by contradiction. So suppose it is, and create a function that's supposed to be onto that like goes from the natural numbers onto your function, and show that it wasn't onto after all. Or you would, yeah, that's pretty much it. That's the classic way of doing it. Or find an uncountable set inside it, and that makes it uncountable. Oh look, my set contains an interval, therefore it's uncountable. So they're the sort of general ways of dealing with it. But if you want to prove from the definition that something is countable, then you need to create a function which goes between it and the natural numbers. You don't have to... Yeah, you just have to get a function that goes from the natural numbers onto it. You doesn't have to be one-to-one to be sure that it's countable. To be infinite, you have to have a one-to-one function. But to be just countable but not infinite, just has to go onto it.
They don't have to be the same function.
Sorry?
You have two different functions, one that's onto...
And one that's one-to-one, yes. Yeah. So, whoa. And a worthy thing to think about is that making a function from that between the natural numbers and it. Oh, I should put z in here. The integers are countable too. Making a function between it and the natural numbers is the same as lining them up in order. It's making a sequence that contains all of them. So just because a sequence in essence is a function from the natural numbers to whatever the numbers the sequence is made of. Yeah. So if you can put them in sequence, then they must be countable. And that's how you prove that the rational numbers are countable. So you go, let's put well, you do the positive rational numbers first, but let's put all the positive rational numbers with denominator 1 in their lowest form. And then let's put all the positive rational numbers with denominator 2 that we haven't already covered. And let's put all the ones with denominator 3 that we haven't already covered. And you just end up covering them all in that way, because they all have to have a denominator. Yeah. So, yeah, I think that's just the rational numbers between 0 and 1, but that's okay. You can run with that. Oh no, the numerators. You do the numerators. Yeah. It works. I know, I've seen it done. I just need to think it through. No, you do all the ones where the denominator and the numerator add up to 1, and then all the ones where the denominator and the numerator add up to 2, and all the ones where the denominator and the numerator add up to 3. Yeah, because there's finitely many combinations of positive integers that add up to 3. Yeah, and you go back and, yeah. Yeah, so if you can map a path that, like a path with discrete steps that covers the whole thing, that does it too, because that's your sequence. But yeah, that path is working your way through all of them by what, because you're going diagonally there, you're going by what the denominator and the numerator add up to. Yeah. Yay. Okay. And as long as nobody has infinitely many, nobody has infinitely many numbers in front of them in the line, they'll all get into Hotel Infinity, so it's okay. Right. So, in general, I think if you're asked if things are countable or uncountable, most of the time you can just say and not give a particularly good reason other than, oh, it contains an interval, therefore it's uncountable. So, contains any of these, right? Yes. Not finite. It cannot be put in one-to-one correspondence with any set of the numbers from 1 to n, where n is a natural number.
Write that, please.
Yeah. Okay, so all the finite sets have sizes which are natural numbers. So one definition of infinite is that its size is not a natural number. And for the size to be a natural number, it means there's a one-to-one correspondence between it and a set which has a natural number of things in it. And so you would say, so the definition of finite for a set, so S is finite if there exists an n in the natural numbers such that there is a one-to-one and onto function f which sends S into 1 to n. That's what it means to be finite. So the set 1, 2, 3, 4, 5, 6, 7 is finite because there's a one-to-one correspondence between it and the set 1 to 7, but so is the set 10, 20, 30, 40, 50, 60, 70, because there's a one-to-one function that goes from it to the numbers from 1 to 7. So this just counts how many of the numbers you have. This function is literally you saying 1, 2, 3, 4, 5, 6, 7, up to n. Sorry? Yes.
So the natural numbers, they're infinite though.
Yep. Because the natural numbers cannot be put in one-to-one correspondence with any of these sets.
Why not?
There's no any n, but you can put the natural numbers in one-to-one correspondence.
Because once you've run out of, it has to be one-to-one, so every natural number has to give a different answer, and once you get up to n, then n plus 1 doesn't have anywhere to go.
But I can include n plus 1.
I know, but you can never include them all. There's always, no matter how big you make it, there's always another number further out. That's the Archimedean property. No matter how big one of these you make, there's always another natural number further on. So you're saying I can include n plus 1. Sure, I'll include n plus 1, but now you have to include n plus 2. Oh, crap, but now I have to include n plus 3, and I'm never going to ever finish things that I didn't think to include, and so therefore I can't do it. Sorry? That's not a thing. At least not here it isn't. Infinity isn't a natural number. Yeah. So yeah, it's not, infinity isn't a natural number. Depending on what context you're in, you're allowed to call it a number or you're not allowed to call it a number, but it's certainly not a natural number. So you can't go to infinity.
So infinite is then just a negation of that.
Yep. That's a definition of infinite. Another definition of infinite is that it's possible to have a one-to-one function between n and your set. Then that makes it infinite. If it contains at least n amount of things in it, then it must be infinite. So I could say, or there is a one-to-one function f which sends n to your set. Yeah. Yeah, oh sorry. This is the definition of infinite. So the definition of infinite is that. But you could also say the definition of infinite is that you can't do that. Or not finite, as per above definition. Okay. So you could define infinite as this, and then define finite as there is not a one-to-one function that sends n into S. Whatever. So, and that's probably a more reasonable way of defining it, because this is referencing n in, to do the thing. Like this is a bit circular, whereas this is nice. There's no one-to-one function from n to S means that it's finite. So saying no matter how you would try and do a function from n to S, you must have at least two of them have the same value inside your S, which means basically your S you have to stop at the end and then start back at the beginning at some point. Cool. I've never thought about some of these things. I've thought about this a lot, but that thing of the looping around, of going, well, I get to the end, I'm going to have to start at the beginning again, that's not something I've thought about before, and it's nice. I like it. I have no idea where I'm up to in time. That clock could be wrong. It's about right. Okay. So I think the only other thing that some people specifically asked about that I haven't talked about is sequences of functions. So I want to know what there is to know about sequences of functions. Before I talk about that, I see just talking about this today, I see what some of the problem with real analysis is.
What's that?
Yeah.
It's really abstract. Like, meaning that you spend a lot of time talking about infinite and really close but not equal, and And there's all these definitions that are really precise for things that you sort of have a natural understanding of what it means. You go, oh, I know what infinite means. But then when you try and sit down and pin down what you mean by infinite, it's really hard to say it in a way that is meaningful and true at the same time. And I can see why that's really struggling. Just talking through this infinite thing, like what does infinite mean? And how do I talk about that? And I can see why that makes real analysis hard, but I can also see why it took so long to fill in some of these rigorous details after the calculus was made. Why it took so long to fill it in, because it is really hard. So what do you mean by as getting closer to something? What do you mean by an infinite sequence? What do you mean by an infinite sum? Okay, so sequences of functions. So my first question about sequences of functions is why it's here in this course, which is ostensibly about calculus, really. And I think the reason is so you can talk about Taylor series.
Sequences of functions, so we can talk about series of functions, so we can talk about power series, so we can...
Yeah. So if you take your Taylor series of order degree n, that's a sequence of functions, and you'd like to be able to talk about that sequence of functions approaching some other function. Okay, so that's what we're going to do. That's the most obvious use, other than just a why not, right? And a what if, which is, you know, the bread and butter of pure math, right? What if and why not? Well, we can make sequences of numbers. Why not make sequences of functions? What would that mean? Yeah, just other than just the big, you know. Ah, yeah. So you can have sequences of combinations of sines and causes. But all the same, I'm going to run with it on the why not front and see where we go. We've got this sequence of functions, and I'd like to hope to be able to say something like the limit of these is equal to a function. I don't know if you're allowed to say that, but I want to be able to say... Sorry? Well, a lot of the time what happens is that people attempt to say it and they attempt to publish it and everyone says, that's stupid. Or you talk to a lot of people at conferences and convince them that it's a useful thing to talk about and it's useful to talk about it in that way, and then the notation and the terminology sticks. Then that's the other way. So it's not like there's a rule book, it's consensus. But it has to agree with everything else that you have already decided is okay. So is it okay to say that the limit of a function is equal to another function? Well, that decides, as long as it matches with the way we talk about limits for numbers, and there's a reasonable way of defining what it means to say that, rather than just wishy-washily saying, hey, this limit is this, as long as there's a rigorous definition of what it means so that you can decide whether it is or is not true, then you can say it. But you also want it to match with the way people already talk about things. So you could have some other crazy thing, but it seems reasonable to reuse the limit notation for functions because it was useful for numbers. So yeah. But us, who are coming in on the tail end of this, having other people who've talked about this for decades/centuries, we want to match with what they think is okay. And not make them feel uncomfortable by using strange ways of talking about things. Right. So sequences of functions, we want to be able to say that it converges to some sort of other function. And so we want to take all the things that we would normally do with sequences of numbers and create ways of talking about them for sequences of functions. Right. So when I talk about sequences of functions and I talk about the sequences of numbers and I talk about the numbers approaching a limit, I talk about the numbers being close to the limit and say that no matter what epsilon I pick, I can arrange for every term of the sequence after a certain point to be within epsilon of the limit. And so I need to somehow be able to talk about distances between functions, which is difficult. And so I'm going to have to talk about distances between the function values at the matching points. And I can think of a couple of ways of attempting to talk about that. And I'm hoping that one of those ways is ordinary convergence, and the other, like pointwise convergence, and the other one is uniform convergence. So this is my guess. My first guess is that if I would say that a function approaches another, that a sequence of functions approaches another function, if no matter which x I pick, that the function values at that x approach the function value of g. So I would say something like
just creating an ordinary sequence of numbers that's just complicatedly defined for functions.
yeah. So most sequences that we care about have been defined as a function of n. But now I'm saying that, yeah, I'm going to create a function which is a function of n, and then I'm going to apply that to each x separately. So pointwise convergence, I'm thinking that for all x in the domain, so I would say that, just a second, fn converges to g pointwise. Is this how it sounds when you do the definition?
Like you're going to need an x0 or something.
Yep. When, for all x in D, and all right, just a second. When, for any x in D, for all epsilon greater than 0, there exists an n in n such that fn x minus g of x is less than epsilon for all n greater than or equal to n. That's what I'm thinking. And essentially what I'm doing is I'm creating a sequence, as you say, of the function values. So I probably should have thought it through that way, but I skipped a step there. And I think that's the definition of pointwise convergence.
Isn't that the definition of uniform convergence?
No, because I picked the point first. Okay, so what I'm thinking is that at every possible x, maybe at x equals 1, then I think about having f1 of 1, and f2 of 1, and f3 of 1, and f4 of 1, and I want that to approach g of 1. And I might have at x is equal to 0, f1 of 0, and f2 of 0, and f3 of 0, and f4 of 0, etc., and I want that to approach g of 0.
The difference between pointwise and uniform is that you pick the epsilon first for uniform.
I reckon. I think the n has to be. I think the n and the epsilon have to both work for everything. Okay. So what I'm thinking now is that maybe there's a way of talking about the function as a whole. At the moment, what I'm talking about is that the function, each function as a whole rather than its individual function values. There's no way of getting around talking about the function values at some point because that's what the function is, but I can try and do it all at once. So if I had to name it, I would call it like, holistic convergence, but I believe they call it uniform convergence.
Why holistic?
Because it works on the whole function simultaneously. If I had to give it a name, just go back in time and Say, hey, great word for this would be holistic convergence. Yes, of course. Sorry? Yeah. So uniform convergence, I think, is the name for it. So what we want is the entire function to sort of converge to G simultaneously. And so I want to pick my distance and have that same, and say that all of the function values are within that epsilon at the same n. So with this one, it may be that it takes me up to n equals 50 to get within epsilon of the G1, and this one takes me up to n equals 200 to get within the epsilon of the G0. And they all have their own n, and so what I want is to be sure that if I'm at the same n, then they're all within a particular distance I'm thinking of. They will all still converge at their own rates, but I just want that there's like a minimum rate that they definitely all get there at the same time. So with something that converges pointwise but not uniform, it would mean that I can never be sure that they converge at the same, that they're within a distance at the same time. There's always one that lags behind the others. That's what I'm thinking there, but we'll get to that in a second. So uniform convergence would be that Fn converges to G uniformly when, for all epsilon greater than 0, there exists an n in n such that for all x in the domain, Fn of x minus g of x is less than epsilon when n is greater than or equal to n. Yep.
The same state, like the same symbols.
But the x has moved down here after the n. Yeah. So what I want to do is I want to choose the distance that I want to be away from the other function, from the target function. Like I want to choose that distance I want to be away from the target function, and I want all of my function values to get within that distance at the same time, at this n here.
So in a sequence of numbers, we can draw like a nice picture of the number line and like the dots. What would be like the appropriate diagram for these two things?
I think we may have to draw all the... I can think of at least one. I'm sure I could think of more than one, because I know two ways of representing the sequence as well. And I drew my sequence as like the y value is what the sequence was and the x-axis was that, but there's another way of thinking about it. Okay, so just a second. I want to compare those two pictures and see what I want to do with them, okay? So I'm thinking that, a picture of, just ordinary sequence, number sequence convergence that I can ramp up to be a function sequence convergence thing. So a picture of number sequence convergence that I might use is to have like an axis of like a number line, and I mark each of the terms of the sequence. And I can say, well, maybe this is A0, maybe this is A1, and this is A2, and this is A3, and this is A4, and this is A5, and they end up here at the limit. So if I just mark where all the A's end up, I end up, to the naked eye, I can't see them being any different from L. But if I zoom in a lot, they will never probably be quite equal to L. Maybe they will, but they'll just get, no matter how far I zoom in, that's my epsilon, I'll always get to this point that every term after a certain spot will all be within my view window. That's my idea of how sequences work. So I have my view window, and there's going to come a point later on, here's L, that, so I've got so A17 ends up in here, and then A18 is maybe out here, and then A20, and then at some point they're all in here. They all get closer and closer. And then if I choose an even smaller view window, at some point the entire rest of the sequence is inside that view window. That's the idea of the epsilons and the n's. So I want to ramp that up to be about functions, and I reckon the quickest way is to say, well, I've got a sequence for each x. Let's just do that at each x. I can just line them all up next to each other. So a picture of function sequence convergence. So what if I have, I'm going to draw this line that I drew earlier vertically. So here's my x-axis of all the x's I could choose. And here's a y-axis. And here at x equals whatever this is, there's a sequence of function values which all go towards this. And here at this x, there's a sequence of function values too. And the idea is being that, like, this is what, and I join them all up together, and that's what F1 is. And then I join these all up together, and that's what F2 is. And so on. And that sort of thing. They may cross over each other, but and the point is that they all start to get close to each other. Which may or may not be straight, but I've drawn it as straight in this one. And there's G there. And so the idea is that in each of them, it may be that it's more bunched up in some places than it is in others. So this sort of level of close togetherness here may be a greater level of closeness here than it is here. And so one of them sort of goes fast. So it may go faster towards the target function in some places than others, and that's not uniform convergence for a given meaning of faster. But if they all sort of go at similar rates, then it should be okay. And usually the only problem is if your function tends to have a discontinuity near the edge, like of its domain.
The same shape moving towards
Yeah, basically.
If it's pointwise, it's sort of, their shape can be more all over the place.
Yeah, they might change shape radically as they go, whereas I think uniform convergence is the change in shape is not as radical. They tend to be closer, yeah. And so the other picture in my head is to try and squeeze them together along their, like squash this all in here and compare how far apart the matching points are. So the idea is that the whole function, the entire of all of these function values is close together, right? It's close to the matching one of G. So I can sort of talk about how far apart they are, and the distance between them all the way along is less than epsilon. So I'm wondering about something that's like this, where this is Fn, and this is the G that's the target, like that. And then because as they go further, they get further apart, and if that pattern continues no matter which Fn I'm up to, I'm always going to have a problem with uniform convergence, because my distance of epsilon, which is like this far, at this end, I don't get within the epsilon. And so at this end, I need a higher end to get to within the epsilon that I do at this end. That's not uniform convergence. That's what I'm thinking about. I'm imagining a Desmos graph that I might be able to make between now and your exam to try and show you what that looks like. I could attempt to do it now. Okay, so these functions, as n goes up, as n increases, these functions get closer and closer to the zero function down the bottom there. But it takes a higher number for this end to end up at zero than it does at this end, and so that's not uniform convergence. That's what I'm thinking about there. I'm not sure. Give me a second. Whoa! They don't change very much. Okay, so this is the Taylor series. This is the Taylor series for e to the x. There's e to the x there. I don't know if this is uniform convergence or not. I think it is. You sure? What about this tail end here? Right, so just for the positive numbers.
Your sequence should have 1 plus the Taylor series.
There we go, look at that. I think that's uniform convergence. I can't be sure. They seem to be getting much further apart. I think on any finite interval it's uniform. I'm not really sure. This is new to me trying to think about it this way. So let's pick an epsilon, right? All right? It won't let me do Greek letters. I should call my epsilon d, because it's a distance, right? Just a second. Oh, for fuck's sake. I can't see the screen. You can, because mine keeps turning itself off. Ah, here we go. Okay, so there's... Oh, just a second. Okay. So there's my distance of d above and below my target function. And so I'm saying that given there should be an n where the entire function is within delta of that. So it's not going to be true on the entire real numbers. It's not going to be uniformly convergent on the whole of the reals, because the bottom end of the odd ones is always going to be going down infinitely far. So, but on this interval that I'm looking at, it looks like I only have to go to n equals 2 to get within the d that I'm thinking of. So if my d was, let me just do 1. Okay. So to get within, and I'll zoom out a bit, to get within that zone of plus d and minus d, I have to go up, damn it. Can I get it to do it with my arrow key? No. I have to go to 3 to get within that. And if my d is a bit smaller, I have to go to 4 to get within that. But once I'm at 4, the whole function is in that zone. Whereas with my other graph, that's my 0, and this function was 1 over x squared, wasn't it? Oh crap, I just need to... I need to just change this to f of x, so I can change the name of the function. Sorry about that. Okay. All right. So with this one, so when my epsilon is this, I wish I could use the Greek letter, but I can't, sorry. Oh, just a second. That feels better. I can call it capital E. Right. Okay. So on the interval from 1 to whatever, I have to get within... Oh, I can't, sorry. I'm going to do it from 1 onwards. Right, just this bit. Okay. So, like no matter what n is, I can never get the entire function to be within the zone. Right? I can get any particular function value to be within the zone. Like if I want this, the function value for this x at 0.1, not 1, but sorry, 1.1, sorry.
Isn't that the matter of then just changing the domain?
Okay, yep, cool. But on this domain, I'm never going to make it work. So on this domain, it's not uniformly convergent. If I include the 1,
Let's say we exclude the 1, so we're going
then it would be uniformly convergent. I'm not sure. Let me see. So I can see this purple line. For that purple line, I can certainly get I can get my function value to be within the zone if I go far enough. But I can't get all the function values simultaneously to be within the zone. Yeah. Because these ones here are out. If my domain is going all the way to 1, if my domain goes all the way to this 1 here, I can never get that blue line to be fully inside this pink zone. And so it's not uniformly convergent. But it is pointwise convergent because I can get any function value for a particular x to get to be within the zone. So this one here, this purple line here, once I get to n equals 7, the function value is within the zone.
Is it not pointwise continuous at 1?
No, not at 1. It could never move from 1. But from the open interval from 1 onwards, then we're good. It's pointwise convergent in the open interval from 1 onwards, but not uniformly.
And that's because of the supreme environment.
Yeah. So let me just go back to here. So my first example is that fn of x is 1 over x to the n, etc. On the domain, the interval, open interval from 1 onwards. Okay? Right, so I'm not including 1, I don't care about 1. So I know that's pointwise convergent, because no matter which point I pick, I can get the function value to be within any epsilon. And on my graph in the built-in computer, on my graph, I can pick whichever x I want. So these x's are already in the zone. And that x, it takes me up to n equals 6 to get within the zone. But this x, it takes me up to n equals 12 to get within the zone. And an x that's even closer, it takes me even higher to get within the zone. So it's not uniformly convergent because different x's require a higher amount of n to get within my epsilon.
Is that not a matter of just having to pick a larger n?
But I can't use the same large n for everything. Like, I can't say that there is no n that's going to get me within the zone for every possible function value all the way along here. Exactly. N would have to be infinity to cover all of them. Yeah. So I can't cover all of the function values simultaneously, so it's not with a single n, so it's not uniformly convergent.
If we change the name
If we change the domain to
anything that is a bit further to the right, do that.
But just as no, you can. You say we're imagining that what if we were thinking of a different domain?
We're thinking of a different function.
Yeah.
These functions have to
Yeah, stop it. What if we were thinking of a different domain here? And that's a good thing. You should always go, well, what if? But right, if we start at 1.1, then yes, no matter what the epsilon is, I could always get the entire function inside that. Yep. And it would be uniform continuous. And so it's that x equals 1 that's the problem with this function. I would imagine that most functions that you could happily think of a formula for, it would be difficult to make them non-uniformly convergent at more than a couple of places if you were just trying to randomly think of a formula that worked.
So is that in general, would that mean if you have a pointwise convergent series,
Yep.
sort of play around with the domain enough, you can generally get it to be uniform?
If the function itself is nice enough, so if you've created it out of like rational functions and exponentials and stuff, then yeah, probably you can pick a domain for it so that it is uniformly convergent.
Certainly, if the function's not continuous, you've got
No.
Yeah.
Yeah. Yeah. So one of the Fourier series ones that happens is that you make it out of sines and causes, and you can create one that the function that they approach is a discontinuous function. And so it's never going to be uniformly convergent near that discontinuity. Yeah. So, yeah. Yeah. And I could attempt to make my Desmos do that. But I don't understand enough about this area to just come up with ones. But I'm quite proud of myself. I've only just learned to use Desmos recently. So, yeah. So on our thing here, I know that Fn approaches the 0 function pointwise, but not uniformly. And I can prove that it's pointwise. So this is going to be my example to prove it, right? I can do as many Desmos animations as I like, but it's not going to prove it. But I believe it now. And so I can prove that it's pointwise, but I need to also prove that it's not uniformly. That's the hard bit. So let's see. I don't know how long I've got to do this. My timer's going for another half an hour, so it hopefully won't take that long. So let's see, let's prove it pointwise. So to prove it pointwise, I need to pick, that I can pick all my x's separately. So I can say that. And it's traditional to say x0 so that people realize that you picked a specific one. Yeah. That's an infinity, not an 8. All right. And then what we want to do is we also want to pick an epsilon. And we want to show that there is an n such that f of x0 minus 0, because that's the function I'm looking for, is less than epsilon. Okay.
Again.
Yes. So what I want is, I want an n such that that's what I want. Okay. So so let's just investigate this. I'm just going to investigate. Yeah. Yeah. So if I could actually say, you know, g of x is the 0 function, and let's say that it approaches g, so it's easier to tell that there's an actual function there. Right. Okay, so let's just think about what this is. You know, for any n, fn of x naught minus g of x naught is 1 on x naught to the n minus 0. So 1 on x naught to the n. I don't need the absolute values because it's a positive number anyway. Okay. And I reckon I can choose, since x is greater than 1, I reckon I can choose an n so that that'll happen. So, so if I want that to be less than epsilon, I'm going to need x naught to the n to be greater than 1 on epsilon. And so I'm going to need n to be greater than the nth root of 1 on x to the n. So, yeah, that's what I'm going to need. So if I choose n such that n is greater than, no. Just a second. I'm actually going to write the maths down. So suppose this is less than epsilon, then we get like that. And so I could do logs, right? Doesn't matter what log it is. Thank you. Right. Excellent. All right, so what we're going to do is we're going to choose our capital N to be that. So choose N to be equal to, well, at least the next natural number after that, at least. I chose our epsilon just right, you might get a natural number. And then if n is greater than or equal to n, then 1 on x naught to the n will be less than epsilon. So fn of x naught minus g of x naught will be less than epsilon. Yep. And so therefore it converges pointwise, since it works for every x naught. Right. So to show that it doesn't converge uniformly, I have to show that if I had picked my n, that I couldn't pick an n that works for every x, right? Because I have to pick the n before I pick the x if I'm doing uniform convergence. So to show not uniformly convergent, I need to show that no matter which n I pick, there's an x. Crap, what's the definition? Yeah. So epsilon is given, and I need to show that there is an n that works for all the x's. So I need to show that to be uniformly convergent. So to not be uniformly convergent, I need to show that no matter which n I pick, there's an x, so that so that the distance is more than epsilon. Okay, so I need to say that, so I need to go let n be a number in n, and I need to show, and epsilon's greater than 0, I need to show there exists an x naught in the domain is greater than epsilon. Yeah. No matter which n I pick, I can find an x so that I'm not within the zone. There's always a little bit of blue outside my zone. It has to be no matter, well, when you do uniform convergence, it says for all epsilon there is an n. So you choose the epsilon first, right? So it's actually this. Let epsilon be greater than 0. And you want to show that there exists an n that blah, blah, blah. But we're doing the opposite, so we want to show there isn't an n that blah, blah, blah. So we need to show that all the n's have not blah, blah, blah. And so therefore we need to let n be anything. No matter which n I pick, I have to show that it doesn't happen. Oh yes, if we show it for one epsilon, it'll be okay. So we can pick in particular epsilon. Yes, that's correct. Because it has to work for all the epsilons, so if it doesn't work for one of them, then we'll be okay. Right. If the handle of the mug is broken, the mug is broken. Okay, so I can pick a number. I might as well just pick 1. Or just something less than 1, because on my diagram, 1 was the distance that was the problem, so a half. Good to have a graph of it, right? So, okay. Well, we should be able to do the same argument we did back there, but backwards to figure out what the x has to be to break this. So back here, it should be like the nth root of 1 over epsilon. Should be the x that is the problem. If the x is smaller than that. Yeah. So back here, it was okay. So we want this to be greater than epsilon, right? That's what the distance we want. Okay. So we can just solve that. So i.e. show that 1 over x to 0 to the n is greater than epsilon. Because that's what this worked out to be. And so that means, for some x naught. So, sorry? We know what epsilon is too. Beautiful. Oh, that makes my maths even easier. So I need the nth root of 2 to be greater than x naught. Okay? So since x naught is greater than 1, and the sequence of 2 to the 1 on n approaches 1, I can pick an n that gets it within the right zone. So I'm just going to need to talk that out. So since 2 to the 1 on n is greater than 1 for any n, yeah, there exists an x naught with 2 to the 1 on n is greater than x naught, which is greater than 1. Sorry, since 2 to the n, 1 on n is more than 1 for any n, there is a number between it and 1. Yeah. The nth root of 2 is never equal to 1, and it's always more than 1. So no matter what it is, there's something between it and 1, and therefore we have found the x we want. And so therefore there exists an x naught with 1 on x naught to the n is less than epsilon, is, yep, i.e. with fn x naught. Yes. Thank you. There exists one that's greater than a half, which was our epsilon. Right. No matter which n we pick, there is an x that makes this more than epsilon, and therefore it's not uniformly convergent.
So that n was picked, we picked epsilon and x.
Yeah. Yes. I think that's a useful way of thinking about it and what order you pick things in, and whether you have to pick them all or just one. So you go, it has to work for all, I pick the epsilon first, I go for all epsilon, and so I need just to pick one epsilon to break it. And then there needs to be an n, so I need to show that there isn't one, which means I need to show that all the n's do something that I don't want. And then work your way through what you have to achieve, rather than, like, it is useful to have the full negation statement, but I find it easier to think through what I have to break and how I have to break it at each level. Yeah, because as you saw there, I got a mix-up, but if I went right back to the beginning and went, right, to break this, I need to find a specific epsilon to break it. Excellent. Now, to break that, I need to show that there isn't an n. Cool, so I need to do something for all the n's. Excellent. And so just work your way forward until you get what you need, rather than attempting to negate the statement, because even if you do that, you still have trouble. So make sure you work through each part of the order correctly. Cool. Well, that will do. I've had a lot of fun talking about that. I hope it was useful for all of you. Yeah. There you go. We are open, so feel free to come and talk to us. I have a feeling Danny is going to be moving his revision, like his drop-in sessions, to the Maths Learning Centre rather than the drop-in zone.
That means any person in the neighbourhood of a person inside the Maths Learning Centre is contained in the Maths Learning Centre?
Sure. I've been talking for too long for real analysis jokes to hit. Yeah, I know. Thank you. Yes, the Maths Learning Centre is open. For any person in there, this is two-dimensionally open, right? For any person in there is a ball around them that is contained in the Maths Learning Centre.